Hi. So today we are going to discuss about the topic about advanced learning techniques. So what we have learned up to now was related to the ordinary machine learning using the deep learning, right, with back propagation and so on. So this is the basic way that we have learned, right, up to now. We have learned how to use uh, sing, single perceptron or single neuron and how to train it, and a shallow neural network. That means a neural network that has like one, two, three layers, not that deep. And then we discussed about the deep neural networks, which may contain much deeper layers, and what are the problems that we face and how to overcome them, and what are the techniques that can be used to overcome them, and so on. So then we have discussed like feed-forward networks, convolutional neural networks, and sequential deep neural networks like LSTMs, RNNs, GRUs, and so on. And finally, we discussed about the transformer neural network, which is also a sequence model. So today we are going to discuss about the uh, different version of machine learning, which is uh, some advanced way of learning other than the pure learning techniques that we have learned up to now. So these are mainly used. These were the technologies that were uh, coming into the front of the development in these days. So once people were much familiar with the existing technologies, so they have come up with many open source machine learning modules. So then they wanted to use those open source uh, machine learning models that are pre-trained for their own application. So then they face some problems, and their data that are there in their models may be different. So how they come up with the solution. So first learning technique that we are learning today is end-to-end learning. So this is just a simple technique where uh, we change the way of learning neural networks, uh, the the paradigm that we were using in the earlier way and the new way, right? So in the earlier time, so when we have limited amount of data, uh, we uh, come up with some intermediate machine learning results, like we come up with some features after running some particular intermediate machine learning models, and using these features, then we run several other uh, machine learning models, and then come up with another set of features, and those features are used again, and so right, and come up with the final uh, outcome that we want to have. In this case, you can see that this image is extracted with features with HOG model. Then we come up with these features, and then mid-level features are extracted, and you can see the boxes that the features are extracted, and these boxes are classified with the support vector machine, and that is how the boxes are the objects are detected in this image. But with the number of amount of information that are available with the current era, like say for example, if you have a lot of photos, and there are even more number of non-related images. So we will discuss later so how those non-related images can be used for as data sets, right? So suppose you have enough data, then you don't need to come up with these intermediate states. So that is the idea of end-to-end learning. So when you come up with these intermediate features, each time you come up with these abstractions, that means, so when you try to identify these features, you are losing some amount of information from this image, right? So from here to here, you lose some amount of information uh, when you're coming into these set of features. So from this set of features, when you're coming up with these set of features, you lose another amount of information. So when you come from here to here, also you lose another amount of information. So if you want to have the highest level of accuracy that is possible with this image, you should directly use this image and come up with the final outcome. So that this is the idea of end-to-end learning, where you have to develop a neural network which can be deep. Like in this case, you can see it is a convolutional neural network. Right? So you can see how this image is converted into different tensors with different sizes, and then some uh, fully connected layers and a softmax layer, something like that. Right? So in this case, you have enough amount of data. So then you can use the end-to-end learning, where the deep learning models can arbitrary, you can set the number of parameters that you want to train. Say you want to have a higher amount of accuracy, and if you have a higher amount of data, then you can increase the number of parameters, and then you can increase the accuracy uh, by increasing some other hyperparameters as well, like the depth and so on. So then you can, using this kind of neural network or a deep learning neural network, you can get higher performance than using this set of uh, neural net, this set of machine learning models that are used as a pipeline to get the final outcome. So this is the idea of idea of end-to-end learning, where you can easily use the initial data set, and you can predict the final outcome as the bycat, right? So instead of having intermediate features, and you don't have to know what are the intermediate features that should be there. So in order to do this intermediate feature extraction, you need to have some domain knowledge as well. But with this new end-to-end approach, you don't have to have an idea about the domain or anything. You just need some the data, and when you correctly tune the module, you can you can come up with the outcomes, right? This is the end-to-end learning. So the other topic that we are coming up with is multitask learning. So another technique that we are going to learn. So in machine learning, for example, news summarization and news sentiment analysis, in both of these cases, you may need to use news as the text input. But in this case, for summarization and sentiment analysis, those are two tasks. So in order to have both of these tasks, in order to run both of these tasks, you have to have two separate labeled datasets, right? Because you have to develop a model, one for the text news summarization and another model for news sentiment analysis. So for both of these models, generally you have to have two different datasets which are labeled. But the problem is you don't have that much labeled data, right? So having labeled data is very expensive and it is hard to find. So maybe you have to do it yourself. So that is very expensive, right? So even if you have a dataset, labeled dataset, you may not have enough amount of data to have a higher level of accuracy to get the outcome, right? So maybe, for example, you may have a highly accurate sentiment analysis dataset, but you may not have enough data for news summarization. So in that case, you will not get higher accuracy, although you can get a higher accuracy for sentiment analysis. So those are some problems that, although both of these tasks are almost same, because you don't have enough data, and because you don't have enough labeled data, you can't achieve them, right? So the multitask learning is trying to run both of these tasks together and run a single model so that both of these models are working better, and even you can add new models easily without much amount of data. Right? So let's see how it's done. Right? Even with a very small amount of data, you can add a new task for the existing trained model so that you can run another task. So that is the idea, right? So when it comes to multitask learning, you can run different tasks together on a single model so that the same model is getting learned and the parameters will be the same, but at the output level, you may have different outcomes, one for summarization, one for sentiment analysis, right? So this is how the multitask learning is working. So with with multitask learning, you will have to run the model uh, with higher number of iterations, and the model may be having should be having higher number of parameters than each of the individual models. But for both of the idea is you want to have higher accuracy or the higher performance numbers better than better than running each of the models individually. Right? So this is an example for multitask learning. So this is a visual language model, right? For future learning, it's published in 2022. So the first task is object recognition. So object recognition means when you look at this image, the text is generated. This is chinchilla. They are mainly found in Chile. So looking at this image, it can identify the object. This is Shiba. They are very popular in Japan. When you see this image, this is, so the trained model should be able to generate this the remaining text. This is a flamingo. They are found in the Caribbean and South America. So this is this is one task. Right? So for each one task, so these are the data points, and this is the one which we are going to predict. So this is another task which is reading and arithmetic. So looking at this image, it can generate the text of arithmetic. This is 2 plus 3. 2 plus 1, it is 3. And looking at this 5 plus 6, which is 11. 3 times 6. So these are the training data set. This is the prediction. It should predict 3 times 6 is 18. Okay? So you can have another task which is counting, like looking at the image, you can say pandas 3. That means there are 3 panda objects. There are 2 dogs. There should be 4 giraffes. So with the single machine learning model, with the single deep learning neural network, all these 3 tasks should be done using the same neural network. Right? So that is the idea of using multitask learning. So not all the tasks that are under the sun can be used as a single multitask learning model, right? Because those are not related. Right? So when it comes to combining some of the tasks as a multitask learning model, so in order to use multitask learning, you have to make some assumptions, right? This is a critical assumption because if you want to have, in order to learn the multitask manner, you should all these tasks should share some structure. That means if it comes to these three tasks that you can see, all of them are images, right? So image recognition is the common structure, right? So when it comes to object recognition, all the tasks are somewhat similar, right? Especially these two tasks. This one is this one is also somewhat similar, but because all of them are related to image recognition, uh, the structure underneath the uh, neural network should be having some similarity, right? So if there is no uh, related structure, that means there is no common uh, structure of the neural network somewhere, that means at a certain level, there's no point of using multitask learning, because if you are using multitask learning for an unrelated task, it would be worse when it comes to the performance. So in that case, it's the single task learning is better instead of using the multitask learning. So when we are using multitask learning, you should make sure that these tasks are sharing something in common, right? When it's related to the task, when it is related to the structure, right? Uh, but most of the cases, there is some structure naturally which is common to almost all the cases, right? So for example, this one, or we may think that this one and this one are not related, but there should be some structure sharing in between these two tasks. So what are those? So generally, these some of the structures that are shared are due to these reasons. So one is because the physical laws that are governing the real world are common to all of the images, right? For example, when it comes to the objects, so for example, when it comes to solid objects are separate from the air and water, right? So and the colors are also have some properties, right? So all of them are related to the physics, right? The physical laws are common. When you put some object on a table or something in the vertical direction, those are affected by the gravity. All those things are common. So the physical properties like gravity, the color, the objects, and like not not having uh, two copies of the same object at the same time. So those things are not related to physics, right? So with the physics that we know, right? So when there's an object, there's only one object. You can the objects are not automatically duplicated. Objects are not getting floated automatically, and so on. So because of these kind of physical laws, there are some underneath common structure in almost all the images. Similarly, uh, when it comes to languages like English, French, and Sinhala, and so on, uh, you will find there are some common nature, maybe the grammar and the use of words and all those things are have some common structure or some hidden pattern. Most of in most of the cases, uh, in almost all the languages. So we don't really know how it has happened. Maybe it is due to historical reasons, or maybe related to the human biology. Yeah, because all of the languages are used by humans. So humans have uh, almost all the humans have similar psychology and physiology when it comes to the humans living in the earth, right? So when it comes to humans, the human generated language should be also having some commonality, right? So when it comes to the things that are invented by the humans are also having some similarity in it. So that's why the multitask learning can be used even without thinking about the structural similarity. Most of the stuff that are there that we see day to day have some common structure. So because of that, you can use multitask learning than we think we can do it, right? So for example, if you look at these three images, like opening a bottle, uh, in this bottle, and this bottle, opening the bottles are kind of similar, right? So you can identify all of them as similar because all of them have a similar structure when it comes to tightening the lid, right? So those things are common, although we haven't planned to do them, right? So because of the technology and all those things are common, everything is common when it comes to these bottles. So because of that, we can use multitask learning for uh, identify or summarizing or whatever thing to do with these images because they should be having some structural similarity. Okay? So let's move to the notations of mathematical representation of multitask learning. Okay? So up to now, I don't know whether we have done this exact notation in our machine learning class. So what we have done up to now, we know that is f theta is an approximation function for the theta parameters given the x input variables and the y as the output variable, right? Variable or variables, right? So this is the single task learning approximation function. But when it comes to multitask learning, this function is not dependent not only on the x given y, but x and zi given y. So zi is known as the task descriptor, which is a representation, which may be simply a integer or something, right? So which is uniquely representing the task which is running, right? So here what we are referring is multitask learning. So when it comes to multitask learning, we don't use this one for the approximation function. We use this one, right? So that because there are multiple tasks for one task, this is correct. But when there are multiple tasks, you should have the task descriptor inside the function, right? So this task descriptor should be a unique one for each of the tasks. So because tasks can be considered as nominal data, right? So because we can say that certain task has a certain value or like numerical value, so we can't use a I as a numerical value, or we can't use them as a label encoding because it is not nominal as well. Like so, we can't say the certain functions are greater than certain functions and so on because they are nominal and there's no order. We can use the one-hot encoding to represent this zi. So this task descriptor, which is uniquely identified the task, can be represented with the one-hot encoded vector. Right? So this one-hot encoded vector encodes a task. Right? So for example, let me so suppose there are 3 tasks. So the first task may be like 1, 0, 0. Right? Sorry for the unclear. The second task should be having the task descriptor as 0, 1, 0. Third task descriptor would be 0, 0, and 1. Each of the task descriptors can be represented like this. So not only the input variables that are so in this example we have taken a convolutional neural network. Right? Here we train the convolutional neural network with input x and parameters theta. Those are the parameters that we are going to find. And more than other than X, we provide the task descriptor Z I. And then we are predicting against the labels Y. Right? Okay, now let's see how the task descriptor is encoded in a neural network. So when it comes to Z, X, you know how to encode this. So this is passed to this layer, and it is passed to this layer, and so on. The information is X information is passed like this. So, but when it comes to an ZI, it may be inserted into a feed for a full dense layer, something like this, to encode the information in the ZI into the neural network. So there are several ways to encode the type descriptor into the neural network. So the first one is known as the concatenation based conditioning, where the input is given, which is the X input, and this is the output, and then this ZI is given as a vector, this blue color vector, and it is concatenated with this input vector. So this blue color one, when concatenated with red color input, there would be a vector like this, right? And then we can have to pass it through a linear layer to match the dimensionalities, which is required for the neural network, right? And then it can be passed as the output, right? The second one is known as additive conditioning. So in the earlier case, we have just concatenated the input with the type descriptor. In this case, in additive conditioning, what we are doing is we are adding the vector value to the input, but because the ZI may be having a different dimensionality, you have to first pass it through this linear layer and get the dimensionality correct, and then you can add this corrected ZI vector to the input after having some linear layer. Then you can add them together, and then you can get the output. So actually, there is no difference between mathematically in information theoretical perspective point of view. There's no difference between concatenating and addition. So if you want to see, so you can look at the mathematics and see that concatenating and going through these layers is also similar to the adding this ZI vector to the input, right? So there's no difference. So in this, instead of simply adding, actually you can multiply as well. This is the multiplicative conditioning, right? You can pass it in the linear layer and get some vector, and you can simply multiply the input with the task descriptor directly, which is this one is may work better because it encodes correct in a much intuitive way, right? So this one is actually better, right? So this one is known as multiplicative conditioning. So in here we are just adding. Here we are multiplicating the ZI with the input data and get the output. And there's another way known as multi-head architecture, right? So you can may remember that in the transform architecture we have discussed, we can have multi-head attention. So for different tasks like task A, task B, and task C, you can have different heads, right? So each of the heads can be represented by the each of the tasks can be represented in each of the heads. And so each of the heads, by running all of these heads together, we can do the multitask learning. Right? So instead of encoding anything, you can run each of the tasks as in different heads, and the bottom layers are shared, right? So those are shared layers. Only the earlier layers can be task specific. That means each of the tasks can be uh, added into different neural network uh, sections, and all of them can be run together so that multitask learning happens automatically. Right? That is another way of uh, achieving the or the implementing the multitask learning. And when it comes to, so up to now, what we have learned was the uh, vanilla multitask learning, right? Vanilla multitask learning means uh, we are actually, what we are trying to do is we are trying to minimize this loss function, right? So minimize this uh, loss function for parameters theta, right? So so this Li is the loss function for the ith task. So I is 1 to t. We are trying to minimize the loss function for these parameters and this data set I, right? For each of the tasks, we have a data set I uh, for each of the data set, and for that particular, for the theta, which is common for the multitask learning, we are trying to get the minimum. We are trying to optimize for the minimum theta, right? So in that case, all these tasks uh, are considered equal because we are trying to minimize the loss function. So we are considering all of these losses as the same for all the tasks. But when it comes to the practical scenarios, for example, if you want to do some natural language processing with a certain mod deep learning model, right? So maybe your first requirement is to have higher accuracy with text summarization, but not with the sentiment analysis or some other mm, named entity recognition or something. So there should be a higher weight coming to the text summarization part. So in that case, we can manually set these weights uh, for each of these losses. Right? So instead of having the same loss in the vanilla multitask learning, you can have weighted multitask learning where you can add weight parameters multiplied with the loss value, so that you are optimizing or you are trying to minimize the loss function by multiplying each of the losses of the each of the loss of the task multiplied by the weight value that you have set, right? So actually you can either manually set the priority with this weight value, or your model can dynamically adjust this during the training process. So we are not going to discuss how this happens, and so it's a bit lengthy, right? So if you want interested, you can look into it. Right? So you can so this weight values can be generally what we do is we can manually set it, or you can train them as well, right? So then this optimization function, or the optimization that we are going to minimize, is getting modified with this weight value, right? So this is how the how vanilla multitask learning works. So we are not going to discuss how this weighted uh, multitask learning works, but the vanilla or the pure multitask learning, where all of the tasks are given the equal weight, how they are done, right? So the first thing happens is that we so there's a distribution of tasks, right? So this is a distribution of tasks, Each of them we can consider as I, right? So there are many number of tasks in this distribution. We get the sample of these tasks known as a mini batch denoted by this letter, right? Capital B. So here what we are saying is that we get some tasks, right? Right. So we don't know actually what are all the possible tasks that are possible with this multitask learning. Actually, what we are doing is we have some tasks like text summarization and sentiment analysis and so on, right? So those are the tasks that are belonging to this B, right? And then what happens is we sample mini batch data points for each task, right? That means, so DI is a distribution of all the data points, right? So then you have a mini batch data point that is relevant to each of these tasks. So for each of the tasks, we should have a set of data, which is a data set, right? So we get the sample data set for training. And we compute the loss on the mini batch. So for each of the tasks, we take the mini batch for the task, and so those are the tasks that we want to do. For each of the tasks, we have allocated the data points. We have got the data sets, and then we are going to compute the loss function, right? So which is known as loss theta b, right? So theta is the parameters, b is the batch, right? So mini batch of tasks. So that means all the tasks that we have selected. What we are trying to do is for loss functions for theta and all the data sets, right? For each of the data set, dbk for which are there in the task A, which belongs to these tasks, right? For all the tasks they are doing is we are taking the loss functions for theta and data set, and we are going to find the sigma. That means we add all the losses for all the tasks, right? So because there's no weight, we are just adding all of them together. If there was a weight, we may have to add a certain weight parameter, right? So because this is vanilla, we are not adding any weight, right? So this is how we calculate the loss function. And then, as usual, as we know, right, we backpropagate the loss to compute the gradient, which is represented like this, right? This is the gradient calculation for the parameters theta for this loss function, right? So which we have defined here. Then you can use a apply gradient design favorite neural network optimizers, like you can have. Generally, the Adam is the optimizer that we are using. You can use it, and then you can optimize the value to get the theta values, right? So this is what we do with multitask learning. Okay, so that is all about, that is not all about, so that this is the theory that we have to know about multitask learning, right? So when it comes to multi-label classification and so on, those are some examples for multitask learning. So now let's move into another type of another advanced machine learning technique. It is known as transfer learning, right? What is transfer learning? The transfer learning was the process of leveraging knowledge gained from solving problems applying to different but related problems. Right? That means when you have a certain problem, machine learning problem, that we have a data set, and that means a labeled data set, which is significant. then you can use this available data set and the model for a related or a similar problem, where we don't have enough data, right? Or you don't have enough computational capacity, right? So in the early, so the available data set is known as source data set, right? And the model that it was trained is known as the source model, right? The problem that we are going to solve, or the problem that we want to solve, is known as the target problem. So we are going to use the source model to get the for the target data and train a model known as target model, right? So what we want to do is what we are going to transfer the knowledge from one task or the domain to another, right? So because we have enough data and we have computed the model with the earlier data set, if we can simply use that trained model for the related data set or the related problem, then you can do it with much less time and with much less amount of data, right? So that is the idea of using transfer learning. So let's say, take an example, right? So in order to train a cat image classifier, right? One thing you can do is you can take the pre-trained convolutional using the ImageNet dataset, right? So what is this ImageNet dataset? So this is a publicly available open source dataset, right? And there are which has like these days around 14 million labeled data points. So 14 million actually labeled images in it. So it's labeling, having that amount of labeled data sets, data points are very expensive, but because this is available for free and because it is open source, you can easily use it. And there are some convolutional neural network models as well, which are trained with these ImageNet. So there are some convolutional neural networks that are trained for the ImageNet data. So in the ImageNet, as I said, it consists of various types of images in the world that you see day to day, right? So when you want to have your cat image classifier developed, you can use this ImageNet trained, pre-trained. So that is known as the pre-training, right? So there are some trained models, convolutional neural network models that are trained with the ImageNet. Right? So you can download such a trained model from internet for free, and then you can do some transfer learning, apply some transfer learning techniques on top of that model, and then you can develop your own cat image classifier, right? With little amount of cat images and within a small time, little time, right? Instead of training for like hours, days, or months, you can simply do it within several minutes or hours by using this already trained ImageNet convolutional neural network, which you can download from the internet. So that is an example of transfer learning, right? So the idea is that in the ImageNet you can find 14 million labeled data points, but for cat images you don't have that much images. So, and for the training, ImageNet is also very expensive. That means you need the huge computers with memory and processing power, and it takes a lot of time, which is very expensive. So when you can download this kind of trained model, you can do some changes on this already trained convolutional neural network and train it for the cat images, few cat images that are available with you, and then you can get very higher accuracy level than and training a convolutional neural network from scratch. Right? So when you are training the convolutional cat image classifier on top of an already trained CNN, it is much higher in accuracy than a cat image classifier that is developed from scratch, right? So that is another advantage of transfer learning, right? So there are several motivations for transfer learning. So one is the scarcity of labeled data. Like as I said, the cat images may be scarce. So because of that, if you can use the an already trained model with higher amount of data, then you can get higher performance, right? And for the model generation is also a problem, right? For example, uh, when it comes to a convolutional neural network trained for uh, ImageNet, that means because ImageNet consists of almost all the types of images, it is highly diversified. That means it is highly generalized. So whatever the image type that you are classifying, it would be working in a very generalized way, right? So you don't have to worry about the generalization or overfitting when it comes to using that kind of pre-trained model. That is another advantage, and also efficiency is also important because uh, you can save the computational resources and the time that you have to train. Basically, there are two types of transfer learning, right? So one is known as the inductive transfer learning, and the other as the transductive transfer learning. So inductive means uh, we are transferring the knowledge from one domain to another domain, right? Like we are the one task is about classifying fruit images. So you are trying to develop another classifier for classifying vegetables. So those are a bit different, right? So we are going to use the transfer learning for transferring one domain task to another domain of task. So that is an example for inductive transfer learning. When it comes to transductive transfer learning, the domain is not changed, but the data distribution may be changed. For example, uh, you are trying to uh, suppose you are trying to model the uh, housing prices, like real estate prices in a certain country, and you have developed a model. So you have developed a model to model the housing prices in America, USA, and you are going to uh, use develop another model for predicting the housing prices in Sri Lanka. So in that case, the parameter distribution may be different, right? So because of that, you can't directly use it. But with transductive transfer learning, uh, you can get the advantage of using the existing model for learning it for training the data in Sri Lanka. Right? So for all of these cases, what we are using are known as pre-trained models. Right? So when it comes to uh, these huge labeled data or unlabeled data, there are some open source pre-trained models that are available that you can download from the internet. So ImageNet is one of them, which is a labeled dataset. And there are some other datasets like GPT datasets like GPT-2, 3, and so on, where those are some unsupervised learned large language models. And that means for the pre-trained models, it can be either a supervised machine learning model or it can be an unsupervised machine learning model. So whatever it is, generally those are very large models where you can download it and then you can develop your own transfer learning on top of that pre-trained models, right? So BERT is also a pre-trained model, right? So let's see how the uh, transfer learning happens with the fine-tuning technique. That means, suppose now you have downloaded an already existing pre-trained model. Now what you are going to do is you are going to fine-tune this model according with your data, right? So you are having some labeled data which may be smaller in size compared to the original data set that is used to train the uh, downloaded model. But now what you are going to do is you are going to fine tune the model uh, so that it is trained for your own data, right? So one problem with fine tuning the model is that uh, if because your data set is very small, it may be very small compared to the data set used for training the pre-trained model, right? For example, if it's a large language model, it may be trained with like petabytes of data, but your text data may be very uh, like it may be hundreds or thousands compared uh, to the petabytes of data that is used for training the large language model, right? So in that kind of scenario, the information or the intelligence that is there in the large language model may get hugely lost during your fine tuning session, right? So he say one way of fine tuning is that you can take the model and you can use a small learning rate and train again for your own data set on top of the weights of the existing model, right? So you have taken a large language model with like 3 billion with 3 billion parameters or something, which are already having the weight parameters, and then you can train with your dataset, like for example, text classification, or for example, news summarization requirement, right? So you have some label data, you are going to train it. So now what happens is, because your dataset is small, if you uh, try to learn it with your dataset, it may be working for your dataset, but it will lose a huge amount of generality that was there in the original uh, large language model, right? So that is known as the uh, catastrophic forgetting. So that means there was a lot of information or knowledge that were there in the original model, but because you have tried to learn with your limited amount of data, it has forgotten almost all the information that were there, like 98% information that was there in the original model, because you have tried to with your dataset. So it may be working fine with your dataset, but it may have forgotten all the most information in stuff that were there in the original model. So that is a big problem when we are transfer learning with fine tuning, right? So researchers have found tried different ways to mitigate this catastrophic forgetting, right? So they have done different things to mitigate it, right? One is known as uh, very small learning rate for all the layers for training, right? So because you are using a very small learning rate, the effect of the weights in all the layers will be very limited. So there's in one way the effect of your data set may be only affecting a little when it comes to uh, changing the existing weights of the parameters in your pre-trained model, right? Say that now you have a pre-trained model uh, and so there are already weights that are there in the pre-trained model. what we are doing is you are training with your data set, and those parameters, because you are using a very small learning rate, these parameters will change only very little, and they will not forget a lot of information, hopefully, right? It may happen or it may not happen. Another technique is using smaller learning rate and for are used for earlier layers, right? So because there are different layers in the neural networks, like this layer, and so on, right? So you input the data here, you get the output here. So you can use a higher learning rate for uh, this layer, and much lesser learning rate for this layer, and a very small learning rate for this layer, right? Because these layers, this layer is subjected to high amount of changes, because the high level features that are there in the neural network are in this layer, right? Uh, these layers are only capturing the lower level information of the neural network, so they have to be changed only a little. If they are supposed to change, they are supposed to be changing only a very little amount, right? Intermediate values are like that, right? Only the last layers should be changed a lot. Other layers should be only changed a little. The deeper you go inside, the learning rate should be reduced, right? So that is another technique. Instead of using a smaller learning rate for all the layers, right? There's another technique known as you only first you freeze all these inner layers. You only train the output layer, right? So first you train the output layer, and then uh, you unfreeze this layer and train this layer as well. Once you have learned this layer and this layer, then you unfreeze this layer and train all these three layers. So that is another technique for training, right? So the idea is that you are, because the highest changes are subjected to the last layer, you are changing this layer, and in order to optimize those changes, you unfreeze this layer, and in order to incorporate these changes, you unfreeze this layer, and so on. Okay? This is another technique. And so there's another way, which is you are uh, keeping only one layer or few layers while keeping the other layers frozen, right? So the idea is that when you freeze these layers, that means you don't have to update the inner features. That means the basic level features. Only the problem is different in higher level. So example, if you are uh, changing the, if you are classifying the fruits with vegetables, maybe the appearance may be having only a few differences, right? So in this case, maybe you can only unfreeze this layer, the final layer, and train it. You may not need to train the inner layers, right? So it was just an example, right? So it's not proven in research or something, right? So if it is related to the higher level features, uh, maybe you can only unfreeze the last layer, last one or two layers, and then while keeping the other layers frozen, and train the model. So that is another way of fine tuning. So how to find which of these techniques are better, right? So you can set the values that the layers that you are training and not training, the learning rates for each of the layers as hyperparameters. And so these techniques and hyperparameters can be selected, and the best model can be selected with cross validation, right? So which one works better for transfer learning? You can do some cross validation with your available data set and find which transfer learning technique works better, right? So when it comes to transfer learning, one of the major problem is uh, overfitting, because you have in your model, your existing pre-trained model has a lot of parameters, right? So if you try to, uh, but your data set or your target data set has only few number of data points. So when you are trying to train a higher number of parameters, very high number of parameters with lesser amount of data, it is going to overfit, right? So in order to overfit, there are not that much techniques available when the number of parameters are so high. You can use regularization and you can use early stopping. So this early stopping technique is generally used because this early stopping technique can actually reduce the amount of time, right? So when the uh, you if you can remember, when the training, if this is the loss and this is the amount of iterations, the training error would be like this. But when it comes to the validation error, it would drop like this and it starts to increase. So if you stop at the bottom of the validation set, so this is the point where you should stop, which is the early stopping point. It's the number of iterations that you should have. So at this point you stop training and take this value as the accuracy loss level of the model, right? So sometimes in some uh, transfer learning techniques, uh, say you have a model, pre-trained model, where there are only 3 layers. So now maybe you can change the architecture and you can add, uh, so you can freeze these 3 layers, these all 3 layers, and you can add new layer here, and you can add new 2 layers here like this. And something like this, right? Y1, you can have 2, if you, suppose you want to have 2 outputs, so you can have, you have 2 layers, 2 parallel layers or something like that, right? So in this case, you are only training these 2 layers. Actually 1, 2, 3, there are 3 layers, right? While freezing all these existing layers. So this is also possible with transfer learning. So because these layers are frozen, there would not be the effect of catastrophic forgetting, but you can initialize these new layers with random initialization or whatever the initialization is suitable, and then you can train these layers with your available target dataset. Okay, so that is about the how the transfer learning works, right? So, but when it comes to transfer learning, there are some unintuitive facts as well, right? For example, this is mainly about the large language models, because those are the uh, large language models are highly used with transfer learning because no one is using a large language model with original with the data you have. Most of them are pre-trained with the unsupervised learning. So that means you are trained with the large language modeling with the unsupervised learning, and then you fine tune it with the supervised learning dataset, and you do the reinforcement learning for uh, smoothly tuning for your own requirements. That is how it is done when it comes to chatbots and all the other LLM related systems. So when it comes to these kind of systems, what they found was uh, if you are training, if you are applying the fine tuning on a randomly initialized, randomly pre-trained, so you if you don't do any pre-training and if you are initializing the vectors at random and then fine tune, you would have an aggregated performance of around 72%. If you pre-train with a huge corpus like petabytes of data uh, with unsupervised learning, and then fine tune with your data, you will get a accuracy like performance like 181.3. So suppose now you have sufficiently large fine tuning dataset. So for supervised learning, and you can maybe say that you can use this supervised learning dataset for unsupervised pre-training as well, right? So in this case, you are using the unsupervised huge amount of data for pre-training, but in this case, you are using the same fine-tuning dataset for pre-training, and then you fine-tune again with the fine-tuning dataset with supervised machine learning. So then still the aggregate performance is around 81, right? So that means although you haven't trained your model with machine learning, so with the huge variety of data or a diverse data set or a lot of data, even if you train it with your own data set with unsupervised learning and so then fine tune with supervised learning, still the performance is not that different, right? That is something that was found recently, but we have to check whether those are uh, working as it is, right? So those are only some of the research. Another unintuitive fact is that as we discussed up to now, we said that we are only trying to freeze the earlier layers and then unfreeze the final layer and try to train with our dataset. Right? So that is the conventional way of training uh, new pre-trained neural network for fine tuning. But some research have found that for different scenarios, like for this one, this is for the image corruption scenario. This is for subgroup shift, and this is known as the spurious correlation. So those are different image related tasks, right? So they what they have found was uh, they have tried with fully fine tuning with all the layers. That means you are unfreezing all the layers and training all the layers, and they have found the accuracies, and they have selected a certain layer, and they have only trained that particular layer. So then this is the uh, accuracy that they have got. So some in this case, image correlation case, if you what they found was if they are fine tuning only the first block, they would have 82% accuracy, while the file tuning was while full fine tuning only gave 79.9 accuracy. So it's not like you have to fine tune the last layer, but even if you try the first layer, maybe for this particular application for image corruption, the first layer may be the most significant, most important layer that you have to fine tune while keeping all the other layers frozen, right? Like you keep these layers frozen and only fine tune this layer. So this has given higher accuracy for this particular application. For this application, only this layer, the layer earlier than the last layer was fine-tuned, and it has given higher accuracy than for the fully fine-tuning model. So how do you know whether this one is the one that you have to fine-tune? We don't have an idea, right? So we have to check one by one if you want to see whether which layer is highly significant when it comes to fine-tune, right? But when it comes to spurious correlation, the last layer is the most significant layer. When you fine tune this layer, it has given higher accuracy than the full fine tuning the model. That means other than training for all the layers, fine tuning all the layers, if you fine tune only the last layer, for this particular application, it has given a higher accuracy. So that means the idea is that selecting the last layer may not be always the best solution for different problems or different scenarios. Some middle layers may perform better when you try to fine tune than the full fine tuning or the last layer full fine tuning, right? So there's another one called Chelsea's recommended default. That means she has given a rule of thumb where the first thing to do is train the last layer and then fine tune the entire network. So in this way, you can easily fine tune as a command rule, right? So this is another rule known as just last recommendation given in a paper, right? Okay, now let's move to the other learning technique known as meta learning, right? So let's look at this statement, right? Now carefully read through this statement. Given a set of training tasks, can we optimize for the ability to learn these tasks quickly so that we can learn new tasks quickly too? That means when we are training the task, how about improving the ability of learning this task by understanding how the learning happens? Not the learn parameters, but how the learning happens, how the updating learning parameters happens. If you can extract that information, you can do the learning task much faster, right? So that is the idea of meta learning. In other words, this is known as optimization for transferability. So that means when you're transfer learning, it is optimizing for the transfer learning, right? So how to optimize for the transfer learning? That is the meta learning. Right? In interest mathematical notation, you can say that we have a data set for training data set, and we are trying to predict this parameters, right? So while then when the network is neural network is converting this data set into this parameter, how this conversion process can be optimized, right? For small data sets. So the idea of the purpose of a neural network is training a neural network is creating these parameters from the data set, right? So how can we optimize this conversion process, with some learning, right? So that is the idea of meta learning. That means learning about learning. When it comes to this learning about learning, there are two views that you can look at this problem about meta learning algorithms, right? One is known as the mechanistic view and the other as the probabilistic view, right? So if you look at the mechanistic view, what it says is that deep neural networks that can read in an entire data set and make predictions for new data points, right? You know it, right? So neural network, what it does is it can read the entire data set and make predictions for unseen data points, right? Training this network uses metadata sets. It uses a metadata set which itself consists of many data sets, each for different tasks, right? That means for each of the tasks, there are different data sets, and it is trained with for different parameters, right? So this is, so we will see how this one is represented again, right? So now let's look at the probabilistic view. So in the probabilistic point of view, we extract the prior knowledge from a set of tasks that allows efficient learning of new tasks, right? So in here, they are talking in the language of Bayesian learning, right? In the Bayesian, we come with this term prior, right? Extract the shared prior knowledge from a set of tasks. That means for all the tasks, there may be some probabilistically dependent prior, right? So all these probabilities for each of the tasks may be dependent on a common prior, right? If you can get this prior, you can train for the other tasks easily, right? So that is the idea. Learning new tasks uses this prior and small training dataset to infer more likely posterior parameters. So what we are going to do is we are going to predict the posterior parameter. So if we have this prior, then you can easily predict the posterior parameters using this prior values, right? So let's look again with the Bayesian way of meta learning. So we are not going deeper into meta learning today. Maybe if we have permit time, if we have enough time, we can do it in another lesson, right? So this is the mathematical representation of the Bayesian view, right? So this is known as a probabilistic graphical representation, right? So these circles are relevant to random variables, right? When these random variables are related to I or j variables, all of them that are relevant to that particular variable are included in a box known as this plate, right? So this is a plate for j parameter. So xij is in this j plate. I test ij is in this j plate. Train ij. All these random variables are there in the j plate. So, but when it comes, this j plate is also on top of this I plate, where phi I and all this train ij, and test ij are also there, right? So these i's are also there in this plate, right? So these random variables have some dependence, right? This xy train ij is dependent on this xij train. This yij train is dependent on xij test. So this test is y test, yij test is dependent on xij test, right? So both this train y train ij and y test ij are dependent on phi I. Phi I is dependent on theta, right? So this phi I is the uh, the task related parameters, right? So these are the predicted values. These are the input values, right? These are predicted input values. These are the x variables, independent variables. So these are the generated model parameters. And all these model parameters are also dependent on this theta parameter. So theta is an it's also a hidden set of parameters which are common for all the I tasks, right? So in this I plate, we are referring to a certain task. So I is relevant to task. I can't write it correct nicely, right? So this is relevant to I is relevant to a task, right? We can train for different tasks. So this phi I represents a set of parameters relevant to the ith task. But all these tasks are dependent with this variable theta. So learning this theta parameter is known as meta learning, right? If there is no common theta, that means if all the phi i's are independent, then we can't do the meta learning, right? This is not there, we can't do the meta learning. If all the phi i's are only dependent on theta and there's no information in the phi I itself, but theta, then we don't need any, then we can easily predict the x and y values for all the tasks, right? That means now what you have to understand is that when you are defining the model parameters, these model parameters may have a common, may be dependent on some common insight parameters known as theta parameter. And also in this model, it may contain some its own parameters. So if the model parameters are independent from each other, then we can't do the meta learning because there are no theta random variables. Right? When theta is there, then we can use meta learning to identify the common information, common structure that is there in between these tasks, right? So now you can see, right? So it's similar to the multitask learning, right? So, right. So transfer learning is a form of multitask learning, right? And meta learning is also a form of is 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 explaining the why the multitask learning is working, right? Okay, so now this is the mechanistic view of meta learning, right? In here, you can see now we have explained in the same way, right? For meta training, we are using two different tasks, two or more tasks, right? So in here, there can be more tasks. So what each of them has done is that we are given some sample images, and then with this test data, it is asking what each of these test image belongs to, right? So we know this one belongs to the category of this category, right? So this is a 5 image classification model, right? classification for with for 5 classes, right? Now it is asking is whether which classes each of these data points belongs to, right? We know that this image belongs to this third category, and this one belongs, this piano belongs to this fifth category. This is also a similar kind of task. You know, this one belongs to something like to this category, and this one belongs to maybe this one, right? And once you have done with the meta training, then you can give another task for meta testing where you are giving another 5-image classifier and another test data set, right? Which is a task, right? And this should be this one, and this one should belong to this class. So unlike the ordinary machine learning where we give data points and evaluate against the y variable, so here we are giving the tasks as the samples for the training. For the training, it's known as meta training. And in order to check the accuracy of this meta model, we are testing with meta testing where we are giving a task to check whether this task is working correctly with this meta model, right? So that is a kind of theory that we have to know about these other forms of advanced machine learning. So we haven't discussed. So these topics are much deep. So we have just covered the basics of these theories, right? So we haven't gone deeper, but if because now you know the know what can be done with these advanced machine learning techniques. When you have a problem like that, you can research and find what should be done with the what can be done, and then you can find how to do it with related to advanced machine learning. Okay? So that is all for the today's lesson.